Okay. Yeah. Okay. So thanks for coming. We are the Italian Mars Society, so the crazy guy would like to go to Mars and with the help of Python. So very quickly on let's say, what is behind all of what we will see. The International Mars Society is managing what the so-called analog. And why we are doing it? Because we would like to show that what the so-called Mars showstoppers are not real showstoppers, but by doing testing, by doing checking procedures, checking methodology, checking technology, you can truly go to Mars, but you have to demonstrate it first on Earth, so that those showstoppers are can be proven to be not real ones. So for studying these things, we are using so-called analogs. And normally those analogs are located in remote areas. For example, the MDRS in the desert of in Utah, and the FMARS in the Arctic. Those analogs have some, let's say, obviously, since you are trying to test extreme environment, placing them in extreme environment on Earth make definitely some sense. But then there are problems associated to it. So basically, the logistical cost become very, very important. Also, you have a very short seasonal use, basically during the summer of especially if you are in Arctic. And because of the, let's say, the overhead associated to the logistics, and let's say the fact that if you have problem in those remote areas, then that can really become a big problem. Then you tend not to really make advanced studies or very advanced technology. You try to really stick to the basic. But anyway, exactly because of this problem, we thought of a different analog to be done in Europe, let's say populated area, where different things could be done. And for example, these things can be a test bed for radiation simulation, for dust simulation that is not possible in these remote area analogs. And this would, the advantage would be that logistical costs are reduced. You can work there all year long. And also, it's a great opportunity for educational and outreach, because you can simply, maybe you can put it in a touristic area and you can invite tourists to look at what you are doing. This is a rendering of one possible place. Basically, we are looking for a place in the North Italy, for example, around Bergamo. This is one possible location where we have been studying. Again, the idea is putting an analog, so an analog of an habitat that could go to Mars for planetary exploration, put it inside a dome, and inside this dome, for example, you could test I don't know, Martian dust storm. I don't know, for example, using giant fan that would generate a dust storm. And there are, for example, university in Denmark that is producing Martian dust, same chemical composition, and so you can have somebody providing you Martian dust. This is the typology. We would like to use inflatable module. So again, test latest technology for the generation of this kind of habitats. And as you can see, there is, for example, also the place to grow vegetable. So the main objective of the project is in field inflatable habitat studies. Again, testing advanced technologies, and also again, very, the outreach is also very, very important. So having something that somebody can visit, it's quite important. And also, the idea is that this research center could become an incubator or a reference place for a small and medium enterprise that could profit of the starting space-related business. The status of the project is that we have created a consortium of university and industries. We have made a detailed project proposal. The problem are the money, as usual. We are talking about something of the order of 3 million euros, and we are looking for funds at the moment. But it's not simple. In the meantime, we are working on something that could be done without a huge amount of money. So we are a non-profit organization. We do not have much money, but with those little money, we try to do as much as we can, profiting of the expertise of the member of the Mars Society. So we are working on the electronic control part and software, and also we have started this ERAS exercise. The idea is the fact that, so since we have started the design of the habitat itself, and we are thinking that the virtual reality that now is becoming effective and profiting of the latest technology that are coming, like for example the Oculus virtual reality headset. We would like to study the design and refine the design of the habitat via this technology. And also you can start anticipating the training of the crew that could go inside this analog habitat by just having them working and, or at least in some sense, start testing the habitat itself before the habitat is being built. And in particular, this can be very useful for the verification and validation of the aspect of the habitat before the construction. So the ERAS development has been divided in these different tasks. The simulation using a game engine, and we have chosen Blender. Body and gesture tracking, the integration with an omnidirectional treadmill. So because the idea is that you have to move around but staying still on the same place, and this is done via a treadmill. We need a support for multi-user because we want to have more than one user, in particular, for example, a crew of 4 or 6 persons interacting among themselves. And one aspect we would like to focus also is the monitoring of the health of the crew, because this could be done in a, let's say, simulated way. And I mean, we think that this could be quite effective, in particular for testing the hardware associated to this health monitoring. This is the project work plan. And again, here you can see basically the things I've said before for what concerns the pieces that are putting together the project. So this is, again, as I said, we are using the Oculus, and we are using Blender for the modeling of the, so basically we had the design of the habitat was done in another CAD, 3D CAD, and we have imported inside Blender. We are using the Kinect for tracking the person that then is inserted in the virtual reality using, skeleton tracking, classical skeleton tracking method. We have, at the end of the story, built our own omnidirectional treadmill because we started hoping that the one that start coming on the market, like the Omni, for example, could do the job, but those things are not yet available, basically. So we have done our own development just because nothing was available on the market. This is our own prototype, kind of a simplified with low cost, but is kind of effective, is doing its job. And the idea is keep improving and changing the design, make it more effective while we are using it, we are trying it with the real crew of people. One of the important aspects of the whole project was the possibility, again, as I said, to have more than one, a crew of more people interacting together. And at the end of the story, it was necessary to create an architecture on which those different people could interact together. This, at the end of the story, was even the thesis of Ezio. Maybe you can say a few words.
Yeah, so this was my thesis project. I graduated last year. So in this project, as you can see, was to design an architecture that was allowing us to have a crew of here, for example, like 3 astronauts, but it can be extended with more. And what we are using is this framework called Tango. So it has this Tango bus, which is accessible from any machine connected to the network. And we have a Python library called PyTango that allows us to access data from Python. So the idea is we have, for example, different PCs or even devices like the Raspberry Pi that read data. For example, the Raspberry Pi reads data from the health monitor, so the information about the health of the astronaut, and it puts the data on the Tango bus, and any other device connected to the bus can access it. And we also have the Oculus and the Kinect. We have Blender, which is at the center of the whole system in a way, because it gets the data from the Kinect, like the body tracking and the gestures, and it reproduces it in the simulation. It runs the simulation. There's like some synchronization so that if an astronaut is walking, the other two can see him walking, or if an astronaut is waving his hand, the others can see it. And all these images are sent to the Oculus, so that the astronauts wearing the Oculus can be like in an immersive virtual reality. So seeing the other two virtual astronauts that in real life they are in a station next to them, but in the simulation we are walking on Mars or in the station. So this is the architecture that I designed. We are also exploring other architecture. For example, now there's a project called Blender VR, which it also works with the Oculus, but it also has a server and handles the communication. So we are also exploring different options, because what we are doing is like really at the bleeding edge, or even we already passed the bleeding edge a while ago. We are like on uncharted territories. We are working with the DK2, and that still doesn't work too well with Blender. So we managed to make the Oculus DK1, the first development kit, to work. The second one, like no one is using it. We're still like no one adopted it yet. So there's still like some problems. And yeah, this is what I was saying with the Raspberry Pi. Is the health monitor. This is used to monitor like a wide range of data related to the health of the astronaut, and it processes the data and sends them on Tango, and then we have like some interface that shows in real time. For example, here you can see the earth rate, the acceleration, and other data related to all the members of the crew. And if, for example, the earth rate goes too high, we can get a warning, and we can make sure that astronaut is actually fine. Maybe it's just doing like some, like, I don't know, some physical activities like walking, or maybe it could be that he's like really tired or running out of oxygen or something like that.
Yeah, one of the important points here is the fact we were very much interested in this crew and this health monitoring, also because some of the things we are doing are kind of not really explored very much. So the idea is, if you take somebody and you put it for 1 hour, 1 hour and a half in a virtual reality, maybe there could be some side effect. So we wanted to keep monitoring somebody doing these things for a long time, especially. Maybe again, we are not never talking about anything exhausting, but again, we are thinking about something that's not been done very much. So we are definitely interested in ourselves in seeing what is going on. So we want to know, okay, you have been in virtual reality for 1 hour and a half walking around, you're still doing fine. So this is also, I mean, on one side, this is useful, we can be integrated with all the rest, and is very effective. So testing this, at the end of the story, we can say that we tested these things, and we decided that we didn't like it. We had one person who was expert it's a first rescue expert, and he was saying, okay, This kind of hardware with this kind of sensor is not effective for monitoring somebody that is moving or doing these things in a certain way. So at the end of the story, we decided on the field that something that on paper looked quite nice for the sensor and the things and the way for. So this was good also in terms of hardware and software, but somebody told us, okay, fielding these things is not effective, and so we decided this is not good. So you see, at the end of the story, you can do something useful by doing this kind of simulation. Please go.
And there's also like a lot of experimentation, because since no one tried to do this thing before, we are kind of the first one on many different like kind of exploration. So we really have to try a lot of different things. We have like a lot of things we find out they just don't work. And another thing about the health monitor is also that it's viewable from within the simulation. So there might be someone inside the virtual base station with a virtual computer monitoring the astronauts. Is also viewable from the astronaut themselves on an HUD, like on inside the like the helmet, and also from people outside. So this is another thing that we are implementing. And yeah, this was like how we imagined at the beginning the idea of the virtual station. So you can see we have like this Motivity, which was just like a prototype, and everyone is wearing the Oculus Rift. We have the Kinects here tracking their movements, and we also have like a projector showing the images if we have like public or just like the people monitoring them. They can see it from here. And this is what we actually did last December. We had our first virtual reality mission called the ERAS 14, and we went in Madonna di Campiglio in the Carlo Hotel. They kindly hosted us for a week and gave us with this nice room where we were able to set up all our motivities. So we stationed here and set up everything and do some tests like on all the equipments. So you can see, for example, here we have like 3 motivities, 1, 2, and 3. We have this one, which is actually a different prototype called Motigravity, but as you can see, it has like some kind of structure that can hold the astronauts up, and it simulates the Martian gravity. So that gives an even more immersive simulation. And yeah, we have computers and all the other tools. Yeah, and here we tested the ERAS habitat. We did like we had a schedule with different mission, and for a week we tested all the like the ERAS habitat, all the methods, the standard, the crew, like the health monitor, and we test everything and see how it worked. It was also a nice opportunity for outreach, because that place, Madonna di Campiglio, is like a touristic place. So where we had a talk there where we show to the public what we were doing. Yeah, this was in this hotel. There's also like this astronomical observatory, which is a private observatory built by the owner of the hotel. And yes, they sponsor. They were also, of course, interested in what we were doing, so that's why they sponsor us. And this it was like our schedule, how it looked like. As you can see, it was like quite busy, like from Sunday to Sunday, and every like morning and afternoon and evening we are spending doing several different activities. We don't need to go through all this, but as you can see, like just quickly, we were looking at the habitat, to the Viera station, which is also, we actually have a stand out there where you can test some of these demos if you haven't done so already. We are just like out there. So we tested the station, we tested the communication, the health monitor. We did a simulated telemedical support session. So we simulate something having like, for example, an accident. And when there was a doctor, which was actually, was it like in South Africa? Yeah, from South Africa, call us on Skype, and by using cameras, assisted the people were telling them what to do to cure the people that were injured. So that telemedicine. We were also working on the ATV design for the simulation, which is another thing you can see in the demo there. We did some EVA, like extravehicular activities, and simulation. We tested the multi-gravity with reduced gravity. We also had a real space suit there, which we tried, like we asked the people to wear it inside the simulation. So they were actually in a space suit, even in the real world, not only in the simulation. And also human factor analysis, teleoperation. Yeah, so we did quite a lot of things. This is the habitat that you can see in our demo there. So we built this 3D virtual reality habitat that you can visit with the Oculus. So what you see here is actually what you will see by wearing the Oculus. So it's like a stereoscopic images. These are the two images that you see with each eye. So when you wear the Oculus, you don't see two images, but you see one image that looks three-dimensional. So you can see that like 3D.
From here, I mean, you can already many of the detail here are wrong in the sense that, but what is nice is the fact that you can go with a rough design, put it quickly together, and then having somebody start working inside and telling you, look, I mean, this is wrong, this is wrong, this is wrong. Just because maybe I'm one already used to something like that. Having an astronaut that already went on habitat would be perfect, but I mean, there are not too many around. But you can have people already that had experience in analog habitat, for example. They can go inside and tell us, look, I mean, there is something wrong here and here and here, and you can start immediately changing, even in real time, your design, so, and changing and modifying things. So, in our opinion, this can be a very effective way of starting, I mean, modifying your design and fit it to the needs of the user, starting from the beginning, and can be quite effective. So you have, again, it's like you are building a house for somebody and you let him start working inside and he's telling you, I mean, this I like, this I don't like, and so on. Or at least you can start discussing why things are made in a certain way. And again, as soon as they went inside, some of those people, at least two of them, were already used to analog habitat, and they immediately told us, look, this is should be modified, this should be changed, and so on. So it was a very effective, I mean, just in few hours we could get a lot of feedback from those people, and I mean, there are many things that need to be changed, so there is already a lot of design, or at least modification that should be done, and we will do them.
Yeah, this is basically test-driven development, because we ask the people to go inside, test it, and see. Since, as I said, this is uncharted territory, we don't have some studies. Well, we have something, but not exactly what we are working on, that can say, this works, this doesn't work. We don't have like best practices or standards to follow. We have to figure out this thing by ourselves, and we do this by testing and see what works and what doesn't work. So this is another demo that we have available there. It's like the ERAS station with the motivity. We have an astronaut there wearing the Oculus, and this is what the astronaut sees. I don't know if you can see it well, but these things here are his hands. So we are tracking using the Kinect the movement of the body. So the virtual astronaut, by putting his hands in front of him, the Kinect tracks that the hands are moving in front of him and shows in the simulation the virtual arms also moving in front of him. So this also means that if the astronaut was waving like that, in the simulation you can see his arm waving like that. And we also did some tests where, for example, inside the station, we connected a webcam, a real webcam streaming from the real world inside the virtual world. So we had a virtual screen inside the virtual station where you can see Franco from the real world talking to them. And this could be used, for example, to simulate the mission support on Earth or orbiting on a station outside Mars, or even streaming from the people, like the astronauts staying in the station to the one staying outside, or different combination. It can be used for communication, like mostly between mission support and the virtual crew in the simulation.
Yeah, this is just the example of the potential of all of these things. You can really do any kind of mixing between real and virtual. And for example, at the end of this month, we will go to Innsbruck. We have our, let's say, colleagues of the Austrian Space Forum that basically belong to the same community. The Austrian Space Forum have a very advanced analog spacesuit. And what we are thinking to do is fielding 2 persons with the real suit walking on a glacier in Austria. We will take the same area that they will walk as basically telemetry. We will take this area inside the virtual reality, this terrain. Then we will have 2 virtual astronauts walking on the same area in virtual reality. Then we will be able to compare. At this point, you can try to mix and understand having people walking on the real area, doing the same path, and having people doing the same path in virtual reality and compare them. And what we want to do is that somebody, let's say the remote mission control in Innsbruck, will coordinate this whole mission with 2 people in wearing, let's say, a mock analog spacesuit, and 2 people in virtual reality, and you will try to coordinate these 4 people that, again, mixing things. So this is something we think could be quite useful, especially for testing procedures, methodology, and again, this technology can enable this kind of testing.
Yes, this was the ATV I mentioned before. So we took this model of a rover. It's not actually a real rover for Mars, but it's something which is quite close to like what an ATV, an all-terrain vehicle that could be used, where an astronaut can go inside. I think there's even place for 2 of them. Yes, and can use to reach remote places which are not close enough reaching by foot. So we can just go on to ATV, travel there, and we try to reproduce this with a virtual ATV that you can drive into simulation to go for an EVA.
To be noted that the terrain that these things are driving are the real one coming from satellite data. So the idea is that we have chosen, or at least considering the available data in the format that can be then imported in Blender of some square kilometer of the Martian surface. But think about that. I mean, if you are organizing a mission, I think it could be quite nice or quite useful that your crew would be able to explore the terrain before going there. So you would be able to explore exactly everything, at least at the level of how things would look like, and you can allow those people to, let's say, explore all the terrain they will see after, I don't know, 2-3 years beforehand. And for example, one of the things you can think of is, okay, look around and understand if there are rock formations that can be useful enough to be a shelter in case of there is a solar storm, for example. Just, I mean, very trivially, it is something like that. I mean, explore the terrain around you and found an interesting spot. This is what you can do. This is something you can have people walking or driving an ATV around there and prepare for the mission they will do afterward.
Or even like getting familiar with landmarks, and surrounding areas. If you see that, like this mountain here, this rock here, you see in the simulation, once you get there, you can recognize the place, you know where to go, or even finding what's the best path to reach a certain place, because sometimes you have a hill which is too steep and too dangerous to go with the ATV, so maybe you want to go around it, so you can find the shortest path. And then when you actually go there, you're already familiar with the environment around you.
One of the other things is that think of this. You would like to provide this crew on Mars with some sophisticated piece of software that could be an electronic assistant, a crew assistant. This is going to be a quite sophisticated piece of software, and you cannot just send these things there without having testing it before. But a software like, let's say, a crew assistant can be completely tested in this environment. So you can think of different, let's say, scenarios. And I don't know, you can think of having people going around and there is an alarm or a problem inside the habitat. You have to call them back and you can check if the logic that you have implemented inside this crew assistant makes sense or not. You can, but again, since you can simulate almost any kind of scenarios, quite realistically, basically, I don't know, I think that 95% of the crucial, I mean, the critical software of this that you will provide to the habitat could be tested inside this kind of environment. So quite, again, I believe quite useful.
And this is what I show you in the first photo is the Motivity, which is a reduced gravity version of the Motivity. So as you can see here, it's similar to the Motivity that we have there. We have the parabolic thing here and the like the ring which holds the astronauts. But on top of this ring, there's not just a ring to hold it in place. We also have an harness which is connected to this metal pole here that is connected on the back of the harness. So what it does is basically lifting up. There are some counterweights which you cannot see from the pictures. There are like connected like here on the sides. There are like 3 counterweights which basically take around 2/3 of the weight off, because Martian gravity is about 1/3 of Earth gravity. So if you weigh 90 kilos on Earth, you will be around 30 kilos on Mars. So what you want to do is having 60 kilos of counterweights taken off from your weight, and we do this by having this counterweight that pulls you up and gets you like lighter, like you feel lighter. And NASA also did something similar, as you can see from this picture, but what we did is even more advanced, because we also have virtual reality. So it's not just like simulation of Martian gravity in a like hangar like this, where looks nothing like Mars. What we have here is both the feeling of Martian gravity and actually what you see with the Oculus. You look around you and you see Mars. So this is a step forward from what NASA did, and is also much cheaper in a way.
We are in contact with this group of NASA that is doing the things, and they are quite interested. And again, they inquired us, like they send us, I don't know, like 100 questions. How you did that and that and that and that and that. So they are also thinking of. They were also thinking themselves to do this kind of step, and they are asking exactly which way. So what we are using in terms of Oculus, Blender, and so on, so on. They wanted to know all the technical detail, and we hope that again we can hopefully keep collaborating with them. And so you see, they are much richer than we are in terms of the equipment they have. But again, at least in this case, we have somehow anticipated them, since they do not have yet, let's say, a link with the virtual reality technology.
And at the end of the ERAS 14 mission, we talk with the crew member that participate to the mission, and we ask them to give us feedback. So what worked, what didn't work, what can be improved, and this is basically like we got like really good feedback, a lot of things that could be improved as it was to be expected, and we find out there are like some problems related with the Oculus. For example, the resolution is not high enough, and there were like some bug where the view at some point was like drifting to the left, even if you were standing still, you will see like rotating. And these are issues known. There are like known issues related to the Oculus DK1, the first prototype, and should be solved by the DK2. And we now got the DK2, but there's a whole new set of issues. So these problems are fixed. There are like new problems that needs to be solved. So it's still like a work in progress. There's always something that doesn't work. And you might wonder what all this has to do with Python, since we are at a PyCon conference, and all that we mentioned has basically nothing to do with Python. The reason why we're here is that we are doing everything in Python. So Python is, we can say, like the main technology that allows us to do all the things we did. Also because we are like a really small team, so we don't have much resources. We cannot afford to hire like dozen of developers working on this. We are just like 4, 5, not even. So with Python, we can do everything quickly and get a lot of things done in like in no time. And this is like an overview of all the Python libraries we use, and even our tool chain. We use Mercurial, we use Sphinx, and all the libraries we found. For example, wrappers for most of the libraries. We made our own for the Oculus Rift. We had one for the Kinect. Blender, which is the tool we use to make the models, and the game engine, the physics simulation, and everything, also can be scripted with Python. It uses Python 3 for everything. So all the scripts in Blender are also Python. So all the ecosystem works with Python, and we use it for basically everything. And we participated for 2 years to Google Summer of Code as a standalone organization. This year we didn't get accepted, but we are still participating under the umbrella of the Python Software Foundation. And we already got 4 or 5 students. We are like selecting students like just these days. And we also applied for the SOCIS, which is something similar to the Google Summer of Code. If you don't know do you know what Google Summer of Code is? If you don't know, it's basically a program by Google where we can get students working for us on an open source project, because all the things we are doing are clearly open source. And we basically get students working for us, and Google pays them. So Google pays this university student to work for us during the summer for 3 months. And this program from the European Space Agency is similar. So we are also trying to get at least a student for this SOCIS program, and have him working on our projects. And for Google Summer of Code this year we got 4 or 5. I'm not sure.
So there is definitely still space for. We don't have many applications for the SOCIS, let's say slot 1. So please, if there is any student around, if you are interested in our project, please apply. I mean, go to this ERAS project page, look at the projects that are there. You can also propose your own if you have good ideas. We are very, very happy. So, but please, we have those money to give to students for a summer job. So please apply with us, and for sure, interesting project will not miss. Will definitely be there. And so please apply. We are missing, especially Italian student. It was always, also in the case of Google Summer of Code, 90% of the students are Indian one, very few from Italy, very, very, very few. So again, this is always something I think we are missing. So I don't think it's very, we tried to contact university, we had in Turin, in Milan, in Pisa, but still the feedback from students is very little. So please apply with us. There is money available for students, so please.
And also, if you are not students, but feel free to spread the word to any students you might know that might be interested. This will definitely help us. And thanks for your attention. If you want to contact us, we have our website, we have our repository on Bitbucket where all the code is, we have the documentation on Read the Docs, and we have a mailing list, and if you use IRC, we also have an IRC channel, which is IMS for Italian Mars Society, on Freenode. So that's it. Thank you for listening. Do we have time for questions?
Yeah, 5 minutes. Thank you, Franco and Ezio. Questions? Come on, it's Mars. Okay.
Well, it's a silly question. I've seen an app, the Cardboard, that works on my Nexus 5, and it does something similar to the Oculus. Since I see that you work with the Raspberry Pis and something on a budget, have you tried that? Is it much different, or?
We are aware of this. We are actually looking at all the different virtual reality headsets coming out these days. We thought Oculus was a good compromise. It's still not really expensive, and because is it true that you can use a smartphone like a Nexus 5 with a cardboard? But on the other end, if you don't have the smartphone already, if you need like free astronaut, you end up having to buy like free Nexus 5, which costs more than free Oculus Rift. And also, it doesn't look as good to have like a cardboard with a cell phone there. But yeah, we are also looking at other options that are like different on the market coming out now. But it's like a new field, virtual reality. We are still trying to figure out standards and everything. So.
But it's definitely true. This is something we are looking at. You see, we started at the beginning with something more, let's say, standard. Let's call it like that. So standard workstation with graphical card connected to the Oculus. I have to say that with the problem, for example, we are seeing now with DK2, you attach it to your Ubuntu box, and it's not working. I mean, it's not recognized. At the same time, so we thought at the beginning that developing on Ubuntu would have been the best, also because, again, remember that everything is based on Blender, and you need Blender running on the workstation, and this is what is creating your, let's say, your graphical environment. Having Blender running on a smartphone, I don't know if you can do it. Maybe you can do it also because your smartphone.
Will stream the image to the
you
the
may
smartphone,
stream the image. So again,
yeah.
this is something we are thinking about. But the main reason also that one.
And also like the libraries, like for the Oculus, there are like lot more people using Oculus, more libraries available. Still not so many, but it's better. It's like one of the most popular one. So there's like more material, more documentation. So it was a easier choice.
But if we understand that the market is going on that direction, and then the support will be best in the smartphone, then we will go also, because we will be forced to go. Also, we are understanding now the support for Ubuntu and for Linux is very, very, very limited. The mainstream is Windows, so in our case we have already problems generated by the fact that we are on Linux. But this is our environment in general. We would like to stay there. But it's becoming increasingly difficult because, again, the mainstream of those devices is becoming smartphone, then Windows, and then Linux is definitely forgotten.
Yeah, it's always a trade-off. You have to, like, every choice has pros and cons.
Other questions? No one? I have a little one. This looks amazing. Consider that it looks on a low budget.
Yeah.
Can you tell us which is the budget?
You can think of You can think of that the main software development here has been done by 8 or let's say 10 students, and Google has given them $5,500. Okay, this is something like $50,000 budget plus. I don't know, 10,000 or even less, $5,000 of hardware, or I don't know, yeah. So this is less than $60,000 worth of.
Amazing, like a bunch of guys here could be your competitors. Yeah. Okay. No other questions. Thank you very much.
And if you want, as I said, we have a stand there. Some of you already tried our demos, but feel free to join us and see, like, try to walk on Mars in virtual reality.